This is another video to explain about the concept of tree. Tree, yeah, we will learn about what is tree in the basic definition, and then we will learn about the traversal in tree, which is pre-order, post-order, and there will be another kind of tree. Maybe I will not explain everything, but you already know about the binary tree or the binary search. We will learn about this one, and the other things I will leave it. Maybe a rapist tree, you will learn about that one, but the other you will just you can try to figure out if you have interest on that one. So the tree ADD. So what is tree? Tree, tree is, yeah, it is a tree when you have the root, okay, and then you have the branch and etc. Then, yeah, if you look at this one, how to make manifest. So yeah, this is bad actually. Yeah, you can do the stock fraud, or you have the Ponzi scheme or bank robbery. This is, yeah, the option to do the make manifest. But we will check what is the tree. Okay, in the computer science, a tree is an abstract model of a hierarchical structure. A tree consists of nodes. Yeah, so yeah, we call this is nodes, this is nodes, this is nodes with a parent-child relation. So parent, so this is parent, and this is child. If this is two level, okay, so this is the parent, this is the child. If you want to look at this one, then this is the parent, this is the parent, and this is the child. If you want to look at the other section, so it's the same. This is the parent, and this is the child. Okay, so that's so that's always the relationship between the upper level and the lower level. This is the upper level and the lower level. So we call it parent and child. We can see this kind of relationship in the organizational charts, or in the file systems, or in the programming environments. So many of those things use tree. So there are some terminology we can define about root. So root means node without parent. In this case, A, yeah, A is the root, because the root here, there is no parent. Okay? No parent. We have internal node, so node with at least one child. So here A, B, C, and F. So A, yeah, here the node we have the one child. B, yeah, have child. C, have child. Okay, and F, have child. Okay, so we go A, and then B, and then C, and then F. They are internal node. External node. What is external node? Sometimes we call it leaf node. We can also say it is leaf node. So node without children. So if it is no children, then we call this is leaf node. See this one, E. E. There is no child. Okay? There is no child. Then this is leaf. I. J. K. There is no child. Okay? G. H. T. No child. And it is the leaf node. Ancestors of node. Ancestor of node means parent or grandparent. Grandparent. So I can see like this one. F is the parent of I. Okay. F is the parent of I. P is the grandparent of I. And then A is the grandparent of I. Okay. So I, and then we will see F. F is the parent. And then I with P. P is the grandparent of I, and I with A. So A is the grandparent of I. We can also look at the depth of the node. The depth of the node means the number of ancestors. So if we have the 1, 2, 3, so the depth of the node is 3. Okay. If we want to see from, let's say, I want to see from its, okay, what is the depth of the tree? What is the depth of the node of its? Then we can say this is 2. Okay, because its to C is 1 and its to A is 2. Okay. So head of a tree, it is the maximum depth of any node. So if you look at this one, A until G, there are 2 depth. A until I, there are 3 depth. Then because it is the maximum, then we call this is the head of the tree. Descendant of node. So we have child, grandchild, and grandchild. Okay, then A and B. So we can see that B is the child of A. Okay, and E is the grandchild of A. And then I is the grandchild of A. Okay. We call subtree because there is a tree consisting of a node and its descendant. So here it is a subtree because there is a node and then there is a child. So this is also another subtree, or we can also see this is also another subtree, and so on. So the tree ADD means there is a position to abstract the nodes. There will be some generic methods. For example, we want to know the length and we want to check whether it is empty or not. And then we can check the position. So where is the position of the element? And we can use iter. Iter means the iteration. For the accessor methods, we want to see the position at the root. We want to see where is the position of the parent. And then we want to see the iterator, so the children. So if there are 2 children, okay, then we want to iterate 2 times. If there are 3 children, then the iteration will be 3 times, and so on. And the integer num children p, it means we want to know how many children. How many children we have? How many children do a tree has? Yeah. In the query method, we will have the boolean whether it is leaf or not, and whether it is a root or not. Then if it is leaf, okay, it is leaf, then it is external node. If it is true, then it is external node. If it is false, it is internal node. Is root, okay? If it is root, then there is no. If it is true, if it is true for root, then it is if it is root, then there is no parent. If it is false, then there is a parent. Okay, that's the meaning by root. Update method. Update method means I want to replace the position P with an object O. there will be any additional update methods. Yeah, if you can define in the data structures implementing the tree ADT. So this is the basic tree ADT. So this is the tree class in Python. So the tree, it is a class, and then we will use the position, if you still remember, position in the doubly linked list. But now this position is for the tree. This is position for the tree. In the position of the tree, you will have the element method. Means you will check whether there is an element on this position or not. And then we want to check the EQ, equal, not equal. Okay. And then you want to check where is the root, where is the parent, how many children do the position have. Okay, the children, so it is the iteration. Okay. And length, it means how many, or what about the size of the tree, whether it is root or whether it is the leaf or whether it is empty. So there's the method. Okay. So in the uh, tree, we have the word traversal. Traversal means travel. Okay. What does it mean by travel? So when you do the travel means you want to visit. Okay. So a traversal means visits. Okay. A traversal visits the node of a tree in systematic manner. So I want to visit every node in the sequence, in the correct sequence. There's a concept we call it pre-order traversal. The pre-order traversal means we will visit the node before its descendant. You know, descendant. Yeah. In the previous one, we call it descendant. It means the child or grandchild or grandchild. Okay, so this is descendant. The application is how to print a structured document. So for example, I want to know how to make manifest. And this is the first. And then you can go to the next. Oh, this is the descendant. So we want to check what is the motivation. And then we go to this part. If the motivation is grid, yeah, then this is the third. And then we go to this section, whether it is ability. And then we go to this section because this after the first child, this is the first child, and then we go to the second child. What about the methods? Okay, so the methods, okay, we go to the first, we go to the second, we go to the third, and then we go to the section. So the algorithm is something like this one. We do the pre-order V. So V is usually use the V to represent the node. Okay, or we can say V is vertex. Vertex. Okay, vertex means vertex. Okay, sometimes people also use the vertex to represent vertex. So we want to visit the visit V at the first time. For each child W of V, for every child, so this is the child, then yeah, we will do the pre-order W. Pre-order W means we will check again to this method. Then after we are here, visit V. So we will visit 2. Visit 2. And then again, for each child W of V, so we have the child pre-order W. Then we will go back here and then visit v. So here we visit 3. For each child, W or V. So is there any child? No, because no child, then we will return back to the previous one. We will return back to the previous one and we go to the next child. That is this one. After we put this one visit 4, then it returns back to this one and it returns back to this node. Then we will visit 5 and so on. Okay, so I hope that you understand about this recursion. This is the recursion. Post order traversal. In the post order traversal, a node is visited after its descendant. After, okay, after its descendant. So the descendant, as I mentioned to you, descendant means the child, grandchild. So grandchild. Okay, and so on. So the application is how to compute space used by files in a directory and its subdirectory. Let's say in this example, it is the directory, the directory in the computer. Okay, you can know that the files is structure. So if it is the folder or directory, there is a folder about CS16, for example, and then you put another folder homework, you put another folder programs, okay? And then in the homeworks you have files. In the homework you have the homework 1, and then you have also another file, homework 1 with no comment. This is homework 1 with comment. And then in this folder programs you have like this file, you have like this file, you have like this file, and then this is just a file to do text. Okay, then in order to do like this post order traversal, you do from the uh, grandchild. Okay, so in this it means like this one, the post order v. So we want to check the child. Okay, is there any child of this v? For each child w of v, post order w, and you can check this one. This is child. Okay, then after you are here, for each child w of v, so this is a new v, there is a child here, post order. Okay, then post order back again. Now here, for each child w of v, so this is a new v. Is there any child? No child. Because no child, then we will do the visit v. So visit 1. And after we visit 1, then we return back to this node. And after we go to this node, then this is another child. Is there any child? No, there is no child. If there is no child, then we will visit v. So visit 2. After we visit 2, then we will return back here. For every child, because there is no other child instead of 1 and 2, then we will visit 3. Okay, and then we go to the next child. In the next child, for each child of v, so this is the child. Because there is no child again from this node, then we will visit 4. And then again to the next child, there is no child, then we will visit. And then we go to the next this one, there is no child, then we do the visit 6. And so on until we finish to all of this file. Binary tree. Okay. We call binary tree it is a tree with the following properties. So in its internal node has at most two children. At most, you know, it means maximum. Okay. At most two children. Or if we call it this is exactly two, it is proper binary trees. Proper. Proper binary trees means proper binary trees. So this is the proper binary trees. Because here we have two children. 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 Okay. So every of this one have two children. Let's say if we have this one with one children, then this is not proper. So exactly two for proper binary trees. It means this is the example of the proper binary trees. The children of a node is an order pair. Order pair means P and then C. So for this one, D and then E. For this one, F and then G. Yeah. We call the children of an internal node is the left child and right child. So this is the left child and this is the right child. There is an alternative recursive definition. A binary tree is either a tree consisting of a single node, the single node, this is just a single node, or a tree whose root has an order pair of children, of which is a binary tree. So this is also a binary tree because we have only one order of children, one order pair of children. Okay. So the application can be in the arithmetic expressions. So for example, you have the A plus B. So we can have this one plus and then A and then B. Yeah. Decision process, yeah, and searching. So we will see some examples later. For the arithmetic expression, okay, we call binary tree. Yeah, it is associated with the arithmetic expression. The internal node is operators, and the external node is the operands. For example, the arithmetic expression 3 for this expression 2 multiplied by a minus 1 plus 3 multiplied by b, it can be expressed like this one. So 2 multiplied by a minus 1, a minus 1 plus 3 multiplied by b. Okay, then this is the, we call this is the binary tree for the arithmetic expression. We can also use this tree as the decision tree. So binary tree associated with the decision process. So the internal node is the question with yes or no, and the external node is the decision. So for example, you want to decide about the dining dinner. Do you want a fast meal? Yes. Okay. If it is yes, then there will be another question. How about coffee? Yes. Okay. If it is coffee, then okay, you can go to Starbucks. No, you can go to Beetle. So Beetle is like maybe Beetle juice. Okay. If you do not want a fast meal, no. On expense account, it means uh, is there any expense for this dinner? Yes. Okay. If there's no an expense, then okay, let's go to Outback. No. If not, then okay, let's go to Shabuhyang, for example. Okay. So yeah, this kind of thing we can use the decision tree. So this is the property of proper binary trees. Proper. Yeah, proper means every node has two children. Okay. So n is the number of nodes, e is the number of external nodes, I is the number of internal nodes, and it is the head. Okay. The property is e equals to I plus 1. E, what is e? E is the external node, and I is the internal node. In this case, e, yeah, internal node and the external node. So let's see how many external nodes. In this case, this is 1, 2, 3, 4. Okay, external node or the leaf node, there are 4. And what about I? I is the internal node. We have 1, 2, 3. Okay, so there are 3. So the E equals to I plus 1. Is it correct? E equals to 3 plus 1. Okay. N equals to 2E minus 1. N is the number of nodes. How many E? We have 1, 2, 3, 4. Then 2 multiplied by 4 minus 1. That means what 8 minus 1, it is 7. So there are 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 nodes. X is less than I, or less than or equal to I. I is the number of internal nodes. So we have 1, 2, 3. So X is the head. The head will be equals to the I or less than I. If I there are 3, then it is less than or equal to 3. Okay, let's see this one. Is it also the same with the proper binary trees? Yes, this is also proper binary trees. Now, if you see the head, what is the head? We have head is 2. Okay. But we know that there are 3 internal nodes. Okay. Then, yeah, this property is still valid because the h is less than or equal to 3. So in this case, h is 2. Yeah, 2 is still less than or equal to 3. H is less than or equal to n minus 1 divided by 2. N minus 1, n is the number of nodes. In this case, we have 7 nodes. 7 minus 1. 7 minus 1 divided by 2. Then it is 3. Okay, so it is still the same with this one. E is less than or equal to 2 power of h. Yeah. E is less than or equal to 2 power of h. H is the head. Let's say this is the head is 2. Then E is less than or equal to 2 power of 2. E is the number of external nodes. So 1, 2, 3, 4. Okay, then it is 4. What about this? The h is 3. Okay. E is less than or equal to 2 power of 3. Okay, that's 3. H is 3. Then E is less than or equal to 2 power of 3, which is E is less than or equal than 8. Is it correct? E is the number of external nodes. So we have 1, 2, 3, 4. Okay. E is less than or equal than 8. We have H is higher than or equal to the log base E. Log base E, what is E? Log base E. So H is higher than or equal to log base 2 E. Log base 2 of E is, we have 1, 2, 3, 4. 1, 2, 3, 4. Then log base 2 of 4. It means this is 2. Okay. And H is higher than or equal to 2. Yes, this is true because we have 1, 2, 3. Okay. In this case, we have 1, 2. Okay. So the property is correct. Or we can have the H is higher than log base 2 and plus 1 minus 1. Okay. It means log base 2 n minus 1, n plus 1. N is 7 plus 1, it is 8 minus 1. Okay. Log base 2 of 8, log base 2 of 8, it is 3. Okay. 3 minus 1. 3 minus 1, it is 2. So h is higher or equal than 2. Okay, then yeah, 2, because this is the head is 2 and this is the head is 3, then this property is correct. Okay. So the binary tree, okay, in the previous one we have the 3 ADT, but we can also have the binary 3 ADT. The binary 3 ADT extends the 3 ADT. So it inherits all the methods of the 3 ADT. The additional methods, we can check the position left, we can check the right, and we can check the sibling. So left means the left of the node, right is the right of the node, and sibling. So whether this and this one, they are sibling. Okay, sibling, sibling, brother or sister, something like that. Okay. And then we can also check the methods. It may define by the data structure implementing by the binary tree ADT. For the binary tree, we can have the traversal as well. So the in order traversal. Okay. An in order traversal, a node is visited after its left subtree and before its right subtree. Okay, what does it mean? So the application is how to draw a binary tree. We have the in order rank of V for X V, and then we will have YV is the depth of V. So this is the algorithm in order V. If V has a left child, so now this is the V. V has a left child, yes, because V has a left child, then now in order left V, in order left of V, then we will check this is a new V, okay, left of V, so left of 2, okay, left of 2. After we have this left of 2, then we will call again the in order V in order of this node. Check if V has a left child. Okay, V has a left child. Then we will do again in order left V. So this the sorry, this is the first is left 6, and then the next is left 2. After we have the left 2, check again here. 2 has a left child. Sorry, left. Now we have the left 2 is 1. Okay. 1 has the left child. Is it has the left child? No, because there is no left child. Then we will visit V. So first is visit 1. After we visit 1, check whether V has a right child. Is there a right child? No. Then because it is no right child, we will go to the previous node and then check. Okay, we have the visit V because there is no other left child for 2. So we go to the right child. So in the first we will visit 1 and then we visit 2 and then go to this one. V has a right child. Yes, this is the right child for. And then we will go to the in order right V. So in order 4. And we call in order 4. Then we go back. to this method again in order v. In order v means, yeah, oh sorry, in order for. So we want to check for has a left child. Yes, because for has a left child, so we will do the in order of that life. So we do the in order 3. So we do the in order 3 and then do again. V now is 3 has a left child. No. Then we will visit V. So we will visit 3. V has a right child. No. Then stop. So we will go back to the previous node and then the previous node will visit V and check, is there any right child? Yes, right child. So this is 5 and so on. So we will do the node by node and the step is like this one: 1 and then 2 and then 3 and then 4 and then 5 and then 6, 7, 8 and 9. So this is the in order traversal. So this can be also used for printing the arithmetic expression. So for example, this is the specialization of the in-order traversal. We want to print the operand and the operator when visiting the node. So for example, print the opening bracket before traversing the left subtree and then print the right or the closing bracket after traversing the subtree. So we want to do the print expression. If V has a left child, then print this one in order left 3. And then print V element. If V has a right child, then do the in order right V and then print this one. Okay. Now let's see this. Okay. So we have the 2 multiplied by A minus 1 plus 3 multiplied by B. Then we want to print this arithmetic expression. Okay. So 2 multiplied by A minus 1 plus 3 multiplied by B. So you will see this one. At the first, we will do the opening bracket in order left. On the left. So it means this is again left and then 2 multiply and then we will go to in order here and then we will print A and then minus and then 1 and then closing the bracket plus 3 multiplied by B. Okay, so this is the sequence with the in order traversal. We can also do this in order, sorry, this is post order. Okay, if you still remember the post order, okay. In the post order means we want to check the leftmost. Okay. We want to check the leftmost, or we want to start from the children, and we want to use the recursive method. So the recursive method returning the value of a subtree, and when visiting an internal node, combine the values of the subtree. So here we have the 2 multiply by 5 minus 1 and then plus 3 multiplied by 2. So we will do like this evaluation expression. We will check whether it is the leaf or not. If it is leaf, then return the element. If it is not, then X is the eval expression left V. Okay, left V, what is it? This one, left V. And Y is the evaluation expression of right V. So this is the evaluation of right V. And then you will go here. Okay, because now if it is minus, so if it is it a leaf? Is this a leaf? No, because it is not a leaf. Then we go again do this one. So X is the left and then Y is the right. And then let's make this one as the operator. And then you will do like this one. There is another kind of traversal, but I think I will not explain in detail. This is a generic traversal of binary tree. Includes a special case of pre-order, post-order, and in-order traversal. Okay, I hope that you understand now. Pre-order. Pre-order means we will start with the descendant. Post-order. We will start with, sorry, the pre-order. We will start with the ancestor. Okay. The post-order. We will start with the descendant. Okay. And then in order, you know, for in order, it is for the binary tree. We will start from the left and go to the right. Okay. So this Euler tour, it combines those three. Okay. So walk around the tree and visit its node 3 times. So on the left, we will do the pre-order. From the below, it is in order, and on the right, it is pre-order. Okay. So if you have interest on this Euler tour, we have a lot of uh, things to do with this Euler tour for the transportation, especially. Okay, for the transportation, there are many things that you can use for using the Euler tour. I will not explain in detail. If you want to use this one for your team project, you can try to figure out by yourself. So the link structure for trees. Okay. If we use the link list, you still remember the link list. The link list, it means we have the element. We have a node. Okay. A node is represented by an object storing. So this is an element, and then sorry, P is the element. We have the parent node. So what is the parent of this one? Because there is no parent of the B, so it is empty. And then the sequence of children nodes. So let's say this is the tree. Okay, this is not binary tree because we have 1, 2, 3. Okay, this is only the tree. If you check this one, P, there is no parent, and then for the children there will be 3. Okay. So it is a sequence of the children. The first sequence is this node. So in this node, the element is A, and the parent is B, and then the child is empty. What about D? This is the sequence. This is a node of, and this node, the element is D, and the parent is B, and we have the children. So D has a children with a sequence of C and E. So this node will connect to this node, and this node element is C, and the parent of C is D, and there is no children of C. So also the same with the E. E is the element, and the parent is this D, and there is no children of E. And F, this case F, this is the element, and then this parent is B, and there is no children. Yeah. So node objects implement the position ADT. So we can use the position ADT to implement these link structures. What about the link structures for binary trees? In the binary trees, we need to make a node, okay? A node that is represented by the object storing. We will see the element, the parent node, the left child node, and the right child node. So let's say we have this binary tree. Okay, we have 2 children. Oh, sorry. We have 2 children. Then for B, okay, we will have no parent, okay, empty. This is no parent. And then the left child node, is this is node, and the right child node, this is another node. So this is the element name is B. And then the node here, we can see the A is connected to the parent. A is connected to the parent, which is B. And then no left child and no right child. So empty, yeah, empty for the left and right. And the element is A. Or what did D? D here, the element is D, and we have another child node, left child, and we have right child. And this C, it connects to the parent. E is connected to the parent, and this is C, and this is E. We can also use array to represent the binary tree. So in order to represent the binary tree with array, so we need to know how to store the nodes in the array. If you still remember, array is using the index 0, 1, 2, 3, and so on. Okay. Now let's say I have this binary tree. So this node A have two children, B and D. It has two children, E and F, and so on. So the idea of this is to store node V is stored at the rank. Okay. A is the array, and then the index we use the rank of V. Okay. What is rank of V? The rank, let's say the V is the root, then it will start by 1. Root, it is started by 1. And then if node is the left child of the parent node, so if the node is the left child of the parent, so the parent it is A, and B is the left child, then the rank node, so the rank of B, the rank of B will be 2 multiplied by the rank of the parent node. So the parent node, what is the parent node? The parent node is 1. And it means the rank B, okay, let me just put here again. Rank B, it means 2 multiplied by 1. 1 is the rank of the root. Okay. 1 is the rank of the A. So it means we will put the position of P, we will put the position of P in the index 2. Okay. What about D? Okay. D, if node is the right child of the parent node, so this is the right child, then the rank node will be 2 multiplied by rank parent node plus 1. Then the rank C will equals to 2 multiplied by the rank of the parent node. The parent node is 1. Okay, then we have 2 multiplied by 1 and plus by 1. Then it is 3. So this rank, okay, this rank indicates the position. So in index 1, we put the index A. In the index 2, we put B. In the index 3, we put D. What about 0? Why empty? Because we if we use the multiplication, like say 2 multiplied by 0, it means it will be 0. So always 0. That's why we will start with 1, because whenever you do the multiplication, you will have a value. Now, let's say now I have E. What is E? E, yeah, we want to know if the node is the left child of the parent node. So it is the left child of B. Then rank of E, it will be 2 multiplied by the rank of the parent node. The rank of the parent node is 2, and the rank of E will be 4. What about the rank of F? The rank of F will be 2 multiplied by the rank of the parent node. The parent node is B plus 1. Then it will be 5. So you will see this is 4, this is 5. Okay. Now, question is, what about E? Nothing. Okay, nothing. C and J, you can get this one. And then G and H, okay, let's see the G and H. Rank of G. The rank of G will be 2 multiplied by the rank of F, which is 5. Then it will be 10. Okay, and the rank of H will be 2 multiplied by 5 plus 1. Then it will be 11. So what is the position in the index 9? Actually, none, because there is no children on the E. Okay, there is no children on the E. What is the index 8? There's also none. Okay, it means if it is not proper binary, this is binary trees. It is proper binary trees, but if there are some nodes which is not available like this one, then it means empty in the array. Okay. Okay, this is how to do the binary trees with array. Okay, so I think this is all for the presentation. So hope you understand about those things. So we learn about the linked lists and trees in this video. Thank you very much for listening this video.